All right. So today's class is sort of, I mean, it's kind of one of these topics that's a little bit math and a little bit physics, and I worry that probably I will not be able to do the math or the physics justice, but we'll see. So kind of my justification for why symplectic geometry is something you might want to do, one justification, is that it's the mathematics underlying what's called Hamiltonian mechanics, or the Hamiltonian formulation of classical mechanics, which basically says if you have a physical system, it has a space of all the states it could be in, that space has a symplectic form on it, and the way you go from the energy function, that really should not be, I should not be getting notifications during class. Anyways, but just a little news for y'all. So the way you go from an energy function, which tells you kind of all the information about how your physical system evolves, to the actual time evolution, is this process of taking the Hamiltonian vector field. So remember here, XH is defined by its contraction with the symplectic form is equal to the differential of the function h. So xh, this is a vector field we get out of the function h, and it tells us the time evolution of the system. So the way states change over time is they move along integral curves of this vector field. Oh, and I wrote the wrong thing there. Along integral curves of the vector field xh. And that kind of in words is Hamiltonian mechanics. So Hamilton's equations are kind of writing out explicitly what that means typically in sort of the case of a particle moving around in a manifold. But it does raise kind of a question, if you're physically inclined, which is, well, why? Why is this the right description of how nature works? And you can say, well, Hamilton told me, Hamilton wrote this down, 200 years ago, and it seems to work okay. I did give an argument for why it matches up with Newton's second law, which some people will call the Newtonian formulation of classical mechanics. So, it's sort of plausible, but why is it right? And I think there actually is a more kind of satisfying answer to this, which is it's actually a consequence of the principle of least action. So I should put like quotes here, the principle of least action. So this is kind of an underlying physical principle that tells you how physical systems are supposed to behave, that works in many situations, and kind of in the world of a particle moving around in a manifold, it's actually equivalent to Hamiltonian mechanics, but in a not totally obvious way. All right, so, what we want to think about is I have a Riemannian manifold M. So one of the things I kind of keep emphasizing is in the Hamiltonian formulation, you only use the symplectic form. You don't use any other data about your manifold, or about your phase space. But if you want to think about like the Newtonian formulation of things, I mean, distances are actually quite important. So if I'm going to kind of do physics in a sensible way, I do want a Riemannian manifold. And as we've sort of discussed with the Hamiltonian, I'm going to assume I have some potential energy function on this manifold that's kind of just, controls how my particle runs around, subject to the fact that it also has kinetic energy. So I have potential energy. I need that Riemannian structure to define the kinetic energy, which is 1/2 m times the square of the length of the tangent vector. So if I have some path traveling around my manifold, at each point it has a kinetic energy defined by the first half of this, that only depends on the velocity vector, and it has a potential energy that only depends on its position. And the action, this is a property that you can either think of it as something that depends on a point in a tangent vector, or since I have this path, you can think of it as depending on where I am in the path. It's the difference of the kinetic and potential energy. So one of the things I actually really like about going through this calculation is you see why the difference between kinetic and potential energy on one side ends up matching with the Hamiltonian, which is the sum of the kinetic and potential energy on the other side. All right, well, usually when you talk to physicists, they'll call this the Lagrangian. For very obvious reasons, I don't really like using that term here, because we're usually talking about Lagrangian submanifolds. And well, it's the same Lagrange, but that Lagrange did a lot of different interesting stuff. And so he has his name on a lot of different things, which aren't necessarily all that closely related to each other. So be aware that this is what physicists usually call a Lagrangian, but just to avoid the possibility of confusion, I'm going to call it the action. All right, well, the principle of least action is that the way physical systems evolve is minimize the total action over the path they take. And this, somehow like it can start hurting your head if you think about it a little too much, because like I'm fixing the beginning state and the end state, and I'm sort of thinking about, okay, how could I have gotten from here to here? I have all these different possible paths. Well, turns out there won't be many of them that minimize the action. There are issues about local minima, etc. So don't worry about that too much. But kind of the key point here is trying to minimize the integral of this quantity over time is what tells me what an actual evolution of the time system is. Some people will call this like equations of motion. Or well, that's, yeah, we'll get there. All right, so this looks kind of weirder mathematically than Hamiltonian mechanics, right? Hamiltonian mechanics is, I look at my physical system, I have an energy function, I feed that through this mathematical process, it tells me which direction I'm going to go, right? And at least it's written this way, this is much weirder. I have to kind of think of two endpoints and think of all possible ways of getting from one to the other, and then say, oh, the one that's, actually physical is the one that, and this is huge, complicated, infinite dimensional space. And the one that's actually physical is the one that minimizes this slightly random looking quantity. But this is very useful because it's a very flexible idea. You can apply it kind of a lot of places in physics. I think a kind of beautiful manifestation of this is you can derive the Einstein field equations that tell you how the metric behaves in general relativity in terms of what's called the Einstein-Hilbert action. So there's, in general relativity, there's an action that depends on what the metric is. So kind of all of space-time has some action that it's trying to minimize. And out of that, you can pull these Einstein field equations, which I guess you would be more properly called the equations of motion. All right. And it's maybe a little unfair to say this is not very practical, but it's sort of, when you think about it this way, in terms of like all possible paths, it at least seems very impractical, right? I'm not going to be able to check every single path and figure out which one has the least action. There must be a kind of better way to do this. And indeed there is. So as I say, you can think about this action as actually a function on the tangent bundle. So it depends on a point and on a tangent vector. And we can actually sort of express the condition of what it means for kind of a very short path to minimize action in a more local way. looks like more like the kind of differential equations you might think about. It looks a little bit more like the Hamiltonian mechanics of I'm at a point, I know what my position is, what my velocity is, and this mathematical process tells me, okay, this is the way you go. And I'll just, it's kind of a pain in the butt to write this all out in a coordinate-free way. I did kind of look it up, and I mean, Canis de Silva, so I'm following Canis de Silva here. I went through it and looked like, okay, what do these equations look like when they're coordinate-free? And it's sort of, well, it's philosophically a bit nicer to write things coordinate-free. It's kind of confusing to actually figure out what's going on. So since I'm only thinking about kind of very local questions, I don't lose any generality by thinking about Rn. And in that case, paths which locally minimize the action are solutions to a particular well-known set of equations called the Euler-Lagrange equations. And Canis de Silva actually derives this. So you can think about, okay, I've got a path. Let me try doing a little perturbation of this path. So I'm going to be a local minimum if the derivative with respect to all such perturbations is 0, right? If I had any perturbation where the derivative moving in that direction was non-zero, well, either by moving in that direction or the opposite direction, I could decrease my action. So I wasn't at a local minimum. And if you're interested in that, I'll let you just go read Canis de Silva. And it's sort of not a hard calculation, but you gotta just go through and do it. And you get what are called the Euler-Lagrange equations. So this is a slightly strange set of equations. On one side, you have the derivatives with respect to space of the action. So taking a directional derivative in the xi direction. And so note here, each side of this equation is just a number, right? You take the directional derivative in a function along a coordinate direction, that's a number. And on the other hand, you look at the directional derivative with respect to the corresponding tangent direction along the fiber of the tangent bundle. That's again a function. And as my path moves along, I look at how the value of that function on gamma prime changes, and I take the derivative of that with respect to time. Maybe I should expand a little bit on the notation here. So xi are coordinates on Rn. So we can get coordinates on the tangent bundle to Rn by, xi up through x1 up through xn are just the points, and then v1 up through vn are the coefficients on the vector ddx1 up through ddxn. So I'm just using the usual isomorphism of the tangent space of Rn to Rn itself, but I have to keep what's the direction along the base and what's the direction along the fiber separate. So xi are the coordinates along the base, vi are the coordinates along the fiber. Okay, so, and as I say here I'm just taking a function and evaluating it at this point. Should also note here, right, I'm taking my path gamma t and taking its canonical lift up to the tangent bundle. Canonical lift of the path. So on the left-hand side, I'm just evaluating this function defined by a partial derivative at that point. Whereas here I'm evaluating it and then taking a time derivative as I move along the path. And if you want to think about these in kind of Newtonian terms, so let me actually go out here. Remember, this action is supposed to be equal to m over 2 norm squared of gamma prime, or let me write v, minus v of, let me write x, the potential energy at v, right? So if I take a partial derivative in the space direction, well, the kinetic energy isn't affected by that. It goes away, and I get minus ddv ddxi, which is the force in that direction supplied by that potential energy function. And on the other hand, if I take partial f, partial vi, then I just get mvi, and then I'm taking the time derivative of that. So this is getting me a component of the velocity vector. I take the time derivative of it, so I get m times the acceleration. So what this is saying, the left-hand side is the force at that point, and the right-hand side is m times the acceleration, F equals ma, that's Newton's second law. So this is all a long, fancy way of writing F equals ma, but it's sort of important because it applies in other situations. Kind of the standard example of this is you have some sort of physical system and it has some kind of constraint. So it actually can't go any direction at once in Rn. So you have something like a pendulum or like a linked set of pendulums. Right? And you have restrictions on where it can go in Rn, and then you're minimizing the action on paths that satisfy those constraints. And so it's not just Newton's second law then, but it's the same formalism of, oh, I just need to find the path that minimizes the action, and I have to sort of interpret this Euler-Lagrange equation in the right way. All right. Any questions? So I also justified Hamiltonian mechanics at the start of the course by telling you that it was F equals ma. So somehow these guys should secretly be equivalent to each other. Though it's sort of, it's not obvious right now what the connection between them could be. Well, in order to do that, we have to switch between the tangent bundle and the cotangent bundle. And the operation that does that is what's called Legendre Transform. And Justin Colt was saying at the beginning of the course that he was really looking forward to this because people are always telling him that such and such is Legendre Transform. And I hope my explanation can be satisfying. I don't think I have anything too deep to say that isn't in Canis de Silva, but we can try to work through things. So this Legendre transform, it's a pretty cool idea from a purely mathematical perspective. So we can start with any R vector space, and we can look at a function from that vector space to the real numbers. And we call it strictly convex if the Hessian, so this is the matrix, which is the mixed double partials, is positive definite at each point. And this should kind of remind you of this stuff about strictly pluri-subharmonic functions, but it's a little bit different because those involve complex variables and their complex conjugates. So this is not just exactly the same thing as strictly pluri-subharmonic things, but it's not so far away either. Well, if that happens, then a little bit of calculus tells you that such a function has at most one local maximum. And the kind of key thing to convince yourself of here is if V is one dimensional, so V is equal to R, right, then a real function from R to R is, it is strictly convex. Strictly convex if it's just convex in the usual sense. Oops. If the second derivative is positive for all x, right? And this theorem that I hope you learned in one variable calculus, that this means that, well, what could happen to the sign of the first derivative, right? Since the second derivative is positive, the first derivative is always increasing. So I can either have that the first derivative is negative everywhere. Well, that's not very interesting. Particularly, there'll be no critical points. Could be positive everywhere. Again, no critical points. Or it could be negative for a while and then positive for a while after that. And then there's one critical point, which has to be a global minimum. All right. So then if you think about a strictly convex thing in higher dimensions, that means along every line in your higher dimensional vector space, you have this convexity. That's what the positive definiteness of the Hessian means, that if I restrict my function to any line, I always have positive second derivative. And if you think about it, you can't have more than one critical point, because if you did, you'd have a line between them and you'd be out of luck. You can see there's only one critical point on that line, so you couldn't have had two critical points of the whole function. All right. So it's also true in this higher dimensional setting that there's at most one critical point. If that critical point exists, it's a global maximum, global minimum, I'm sorry. So it has at most one local minimum. If you only have one local minimum, it's global minimum. In that case, we call the function stable. So when I was talking about these functions here, this situation is stable and this situation is unstable. So, right, examples of this would be e to the minus x, e to the x, and then x squared, which is kind of a happy minimum, happy medium between the two that actually has a minimum. All right, so what Legendre transform is, it really is just, I have this function from V to R. I can look at its derivative at each point. So its derivative at each point is a map from the tangent space of V, which I can identify with V canonically, to R. So every point in V gives me a linear map from V to R, or an element of V dual. this is E, dfp is in V dual. All right, and if I look at the difference, f of v minus the pairing of v and this derivative, that's again strictly convex. I subtracted a linear function from it, so I don't change any of the second derivatives. The Hessian stays exactly the same. And of course, this function has a critical point at p, because I specifically killed off whatever the derivative of f at p was. So that's a critical point. The only way that a strictly convex function can have a critical point is if it's a global minimum. I wrote local, but I should actually say global. A little space here. Okay, so let me just actually add this in. This is called the stable set. So all the functions, so we saw here that all of the elements of V dual that appear as derivative of f at some point have this property that when you think of them as linear functions and subtract them off of f, you get a global minimum. So we can just say, oh, look at all the elements of V dual such that when you subtract them off from f, you get a global minimum or a local minimum, same thing. So we just discussed that if I define a map from V to V dual by V gets sent to the derivative at V, that has to have image in the stable set. And in fact, it's an isomorphism. So I can invert this function on the stable set by sending the element L in V dual to the unique point, which is the minimum of f minus that guy thought of as a function. And I can also equip the stable set with a dual function, f dual, which sends an element of V dual to the value of that actual of the function f at that minimum, but minus that. You know, sometimes this happens in dualities. You have to stick in a minus sign. So let me just kind of emphasize what's going on here. I have V. I have this stable set SF in V dual. So I have a function this way, which is consider the derivative of f at V. So V maps to that. I have a map back the other way, which is L gets sent to the minimum point of f sub L, which is by definition f minus pairing with L, thought of as a linear function. Yeah. All right, and then both of these guys have functions to the real numbers. Here I have the function f, which was part of my original definition. And then here I have the function f dual, which is sorry, let me actually give this a name. F of V, d f sub V. dual of f of L is equal to this minimum point, and f dual of L is minus the value of f sub L at L dual of L, which is the same as minus the minimum value of f sub L. All right, and as suggested by the name duality, if I swap the role of V and V dual and F dual, I will get back the original. These guys will swap. There's sort of a minor asymmetry in the fact that I have to take this stable set, but it's fixable. I could be very careful and make this symmetric, but let me not worry about it. All right, so are there any questions about this algebraic setup? And this is one of these things that like can be a little mind-bendy, but if you kind of think it all through, it's actually kind of amazing that it works. To me, it's amazing that it works. So are there any questions? All right. So the most basic example to keep in mind is if V has some inner product on it, then I can look at norm squared. And for my own reasons of taking derivatives, I'm going to put 1/2 norm squared. And if I do that, well, what's the derivative of that at a point F? It's pairing with that element F thought of as a linear function. So when this function is defined by an inner product, I exactly get the function from my vector space to its dual, which is defined by that inner product. So this is actually nice. In particular, this is, you can think of this as the way of getting the inner product back from the norm, the L2 norm with respect to it. So kind of algebraically cool from that perspective as well. You don't have to say all this nonsense about the parallelogram law. All right. So for us, what this is going to be is this is going to be the operation that gets us between the cotangent bundle, the tangent bundle and the cotangent bundle, or in physics terms, between velocity and momentum. So when we have a particle moving in a Riemannian manifold exactly as before, well, we have this action functional on the cotangent bundle. And what we want to do is we want to do fiber-wise Legendre transform. And I am sorry about this. If there's anything that's more confusing than Lagrange's name being on everything, it's also that like there's a bunch of stuff that both Lagrange and Legendre worked on. And so they're not, whoa, shit, sorry. Just had a minor spill. All right, break time while I clean up. I will be back in a moment. All right, so sorry, we're back. Did anybody have any questions about that came to them during the break? So let me just summarize again. When we have a vector space, a strictly convex function to R, that gives me a natural map to the dual space, which well, it might not be an isomorphism, but it'll be a bijection with a stub set called the stable subset. And that map is just taking the derivative of this function f. And you can legitimately say, well, hey, wait a second. Aren't you just going to use the case where that function is a norm with respect to an inner product, and isn't your map just going to be sending a vector to its dual under that inner product? And the answer is, well, yeah, pretty close. But it's always better to do these things in a coordinate independent way. So, I might change coordinates in some way that doesn't necessarily respect that inner product. And Legendre transform will kind of work in a natural way and be well behaved. And I don't want to be kind of confined to this most kind of rigid way of thinking about things. That's where you can kind of see that all of these things are the same, that Newtonian mechanics is the same as Hamiltonian mechanics, is the same as Lagrangian mechanics. But part of the point of Lagrangian and Hamiltonian mechanics is then you get to exploit the fact that those don't have to work in sort of the simplest coordinate system, and you can change coordinate systems in various interesting ways that are useful. All right, cool. All right, so now what we're going to do, we're going to go back to our setup of Lagrangian mechanics. We're going to think about the tangent bundle to a manifold, and we're going to think about this action functional on the tangent bundle, which is m/2 times square of the length minus the potential energy. And we're going to do Legendre transform with respect to the action as a strictly convex function on each fiber. So, right, on each fiber, this is some constant plus norm squared times m/2. So it's a strictly convex function because norm squared is strictly convex. And when I do Legendre transform, well, exactly what I'm going to do is I'm going to send v to the covector of m times pairing with v. So what you should think of this as Legendre transform is the thing that takes in the velocity and spits out the momentum. And kind of the right way of thinking about momentum is it's the derivative of kinetic energy with respect to velocity. Again, somehow like that's both, if you don't think too hard, kind of obvious from a naive calculus perspective, but it also sort of gives you this, it works in a more sophisticated way as well. All right, well, we also can take the Legendre transform of our function, right? And that's defined as minus the minimum of this energy function minus the linear function of the momentum thought of as a linear function on the set of velocities. And if you follow that through, what you're going to get is exactly the Hamiltonian. And the reason that the sign switches on the potential energy is from the perspective of the Legendre transform. That's just a constant. It's constant on the whole fiber. So constants get negated. But when you apply the Legendre transform to 1/2 norm squared, you get 1/2 norm squared for the dual norm on the dual vector space. So you exactly get out again. I'm slightly worried that I messed up where the momentum goes here. So I'm going to have to think about that for a moment. Sorry, I think I actually want 1/2n here. So if you multiply, so let's do this in kind of world. This is worth checking here. So I told you here that if you take 1/2 times norm squared, you get the derivative with respect to this guy. In general, if I have some norm and I take f is equal to m/2 norm squared v, then, well, the derivative of f is equal to m times the inner product with a v. So that's going to be my map. LF of v is the linear functional m of this guy with itself. And now what I have to think about is what's LF? Oh, sorry. So I think exactly where I'm going to go wrong is that then LF of pairing with a function is 1/m. Pairing with a vector is 1/m times that vector. Just inverting this guy. And I think that was where I had run into trouble on that previous page. So F star of this guy is equal to minus the minimum value of m/2 squared minus this guy. And where is that going to have a minimum? So the derivative of this guy, this is f sub is pairing with v. Derivative of f of this pairing with v is m. I'm being bad. Yeah, sorry. That's probably exactly where I got mixed up. So sorry. I'm probably going a little too far down this rabbit hole, but I want to do this calculation right. When I have some element of v, which I'll call w, pairing with that guy gives me a linear function, an element of v dual. And by definition, the value of f dual on that is minus the minimum value of is m/2 times norm squared minus v comma w. So the derivative of that is m times this guy minus pairing with w. So the minimum is when mv is equal to w, or where v is equal to 1/m w. right, so I get minus, and some of all of this is to see where this half actually turns out to be pretty important. I get minus m over 2 length squared of w divided by m minus 1 over m w. So I get minus m over, minus 1 over 2m length of w squared plus, because of the minus sign in front of the min, plus 1 over m length of w squared, and the half comes in to save the day. I get 1 over 2 m length of w squared. All right, so the mass switches where it was, right? The key thing here is somehow that half stays in the game because it gets canceled when I take the derivative. But if I had started with m times the length, I get 1 over m times the length. So there's sort of a dual scaling here. Okay, so this is all just to explain why I have that 1 over 2m down there at the bottom. Okay. But since the potential energy is just a constant, right, if I had thrown in a constant here to F plus some constant C, right, then where would anything have changed? I would have gotten minus the min of this guy plus C. That derivative doesn't change, that doesn't change. So I get minus this guy. Oops. Minus C, minus C, minus C. So if I add a constant, that constant switches sign. And when I put in the action, I get the Hamiltonian. Okay, great. So this is kind of the thing that needs to be in bold. The Legendre transform of the action is the Hamiltonian. So if you believe Lagrangian mechanics, this is why Hamiltonian mechanics is right. If you believe Hamiltonian mechanics, this is why Lagrangian mechanics is right. All right. So there's an actual mathematical theorem behind this. Let me actually write it out properly. I don't think I said. Oops. Probably I'm going to say it down here, but let's actually say it. Oops. Theorem. A path gamma satisfies the Euler-Lagrange equations, Euler-Lagrange, for some action F if and only if the Legendre transform of its lift up to the tangent bundle, so the Legendre transform with respect to the action of the path, sorry, let me call this path x of t. I decided to use x of t below. So all of this stuff depends on t. X dot of t. So I can apply the Legendre transform to the position the path takes me to and its velocity vector, thought of as a point in the tangent bundle. This gets me a point in the cotangent bundle, which I can think of as the point that the path is at and the momentum of the path rather than the velocity. And I satisfy the Lagrange equations if and only if this bundle is an integral curve of H, which is the Legendre transform of this action. Okay, so the words I'm using here all come from physics, but this is an abstract result about differential geometry. That if I have an action on the tangent bundle, it's got to be strictly convex along the fibers. Then I have this Legendre transform map to the cotangent bundle, and the image of a solution to the equations of motion, the Euler-Lagrange equations, is an integral curve of, oh, I didn't say quite the right thing, an integral curve of the Hamiltonian vector field xh with respect to this Hamiltonian. And let me just emphasize here, this is with respect to the canonical symplectic form. The cotangent bundle of x. Or I think I switched using him. All right, so obviously this is very heavily motivated by classical mechanics, but it's a purely mathematical statement where it, doesn't, this statement being true doesn't depend on the function f having any particular physical interpretation. It just depends on it being strictly convex along the fibers. All right, cool. So this sort of explains why, again, you've got to believe one of Hamiltonian mechanics or Lagrangian mechanics. You have to either believe this stuff about Hamiltonian vector fields giving you time involution, or you have to believe the principle of least action, but they're mathematically equivalent. So you only have to believe, take one of them on faith, and then the other one is a mathematical consequence. And I think most people would say the principle of least action is the one you should take on faith, but that's kind of a pretty universal thing in physics, whereas Hamiltonian mechanics seems a little more contingent. And I actually read a whole paper in a journal about the philosophy of science about why Lagrangian mechanics is more basic, but I'm not sure I can actually explain what that told me. All right. So let's think about this. As I say, we're going to take, oh, I meant to rename the path. Path I'll call x, depending on t. We have this lift up to the tangent bundle where I take my base point being my point x, and then I take the velocity vector of the path. So that gives me a path landing in the tangent bundle, and I can take its image under this fiber-wise Legendre transform, and I get a path in the cotangent bundle. And I want to compare what it means for that original path to satisfy the Euler-Lagrange equations and what it means for its Legendre transform to satisfy Hamilton's equations. All right, as before, everything is local, so I might as well assume I'm on Rn. And Hamilton's equations have this nice form, right? We have this explicit description of the canonical symplectic form, it's dxi, sum of dxi, which dxi. So if you trace through what being a Hamiltonian vector field means, well, it means that the derivative with respect of xi with respect to time is equal to of h with respect to xi, and the derivative of xi with respect to time is minus the derivative of h with respect to xi. And we ultimately want to show that this is equivalent to the Euler-Lagrange equations, which I've just recopied here for your reference. The space derivative with respect to the original coordinates of f is the time derivative of the derivative of f with respect to the coordinates along the fiber in the tangent bundle. Okay, so equation 1 is just an algebraic statement about Legendre transform, right? So I'm taking the derivative of the Hamiltonian along the fiber directions and thinking of that as an element of the dual, as an element of the tangent space at that point. And I'm saying, oh, that's the same as the velocity vector of my curve. That's just the inverse Legendre transform. So I'm now applying Legendre transform with respect to h, and it's sending the momentum back to the velocity. So the fact that the first Hamilton's equation says the velocity is the Legendre transform of momentum with respect to h. And that's because I defined momentum as the Legendre transform of velocity with respect to the action. All right, that part's automatic. So I just have to show that the Euler-Lagrange equation is equivalent to that second Hamilton's equation, which is that the derivative of xi with respect to time is equal to minus the derivative of the Hamiltonian with respect to space. All right, well, that's not so hard, but I really feel like Candace de Silva does not explain this very well. Right? It's one of these things where it's not a hard calculation, but she writes down this equation, which is correct, that the Hamiltonian of xc is equal to the inner product between the velocity and the momentum minus the action. So, right, this is saying that if the Hamiltonian is kinetic plus potential energy and the action is kinetic minus potential energy, well, the sum of the Hamiltonian and the action is just 2 times kinetic energy. So this is saying that h plus f is 2 times kinetic energy. Which is the same as the pairing of the velocity and the momentum. All right. And now Candace de Silva takes this equation and says, okay, we're going to differentiate this with respect to x. But there's this issue that there are 2 things that differentiate with respect to x could mean, and they don't mean the same thing. One of which is differentiate with respect to x holding x prime x dot constant, and one of them is differentiate with respect to x and hold xi constant, right? And then those end up those aren't the same, and so when you differentiate the 2 sides, well, on the right hand side you can just do things totally naively. You're just differentiating f, taking the partial derivative in the x direction, And this inner product, you're taking the derivative, x prime is held, x dot is held constant, c changes, and you just get x dot with the derivative of c. On the left-hand side, well, there's the derivative of the Hamiltonian holding c constant, and then there's an extra term that comes from the chain rule for the derivative of the Hamiltonian with respect to c and the derivative of c with respect to x. Now again, by this Legendre transform here, these two terms are the same, so I can just cancel these two terms, and I get that the derivative of the Hamiltonian with respect to x is equal to minus the derivative of the action. And again, if you're sort of thinking about this in terms of the like potential and kinetic energy, like the kinetic energy is killed, it doesn't change when you change where you are in space. So its derivative is 0 with respect to space. And so you're just getting that, you're only getting the derivative of the potential energy on the Hamiltonian side and minus the potential energy on the action side. All right. So once you have this equation.
I have a question.
Yes.
Can you just say again why you have these two choices of holding c constant or holding x dot constant?
Well, I'm at least, yeah. As I was saying that, I was like, oh wait, are those actually different? I had a momentary pause on that, but you at least would have to explain why they're the same, right? That you have this Legendre transform. So like you're on Rn, you're using that you've identified all of the, I mean, because your metric might not be the obvious flat metric, right? So you're on Rn, you're identifying all the tangent spaces are on Rn in the obvious way using the vector space structure, but those don't all necessarily have the same inner product on them, right? And on the cotangent bundle side, well, the cotangent bundle is also trivial. You can identify all of the cotangent spaces, but the statement, like the metric is not the obvious flat metric on Rn, is exactly the statement that sort of those two trivializations aren't going to match up. Right? In order for those trivializations to match up, I think you would actually need the metric to be the obvious flat metric. If you sort of move around in Rn, you're sort of moving your tangent vector around using just sort of the coordinates on Rn. Its length is changing, and so its image under the Legendre transform is not going to be just move around in the cotangent space in the obvious way. So the point is somehow that like this derivative with respect to space is something that depends on the trivialization, depends on the coordinates I chose, in a way that isn't true for the derivatives in the fiber direction. That makes sense?
Yeah, thanks.
Yeah. I mean, it's sort of, right, like identifying tangent spaces at different points, right? The thing that should freak you out here is, I have a function on the tangent bundle or the cotangent bundle, and I'm taking derivative with respect to coordinates on the base. I have to think carefully about how I lift those up to the whole bundle. And by assuming I'm on Rn, I can do that, but it's not really canonical. All right. But, so what this argument is sort of saying is, yes, but on both sides, you will get such a contribution, and those contributions will cancel. And you'll get this spatial derivative of the Hamiltonian is minus the spatial derivative the action. All right. So I can take this. This is the second Hamilton's equation. Sorry, this is. Right, this second Hamilton's equation exactly used the space derivatives of the Hamiltonian minus those. Right, I sort of wrote this in a kind of funny way. But these guys being equal is H2. And these guys being equal is the Euler-Lagrange equation. And what we've shown, right, this bottom equality, that's this guy we just checked. And this inequality, it's one of these things where you write something and then you're like, wait, what? Why is that right? But I think this is right. This again, this top equation, this is just the definition of Legendre transform. So, right, you're taking the derivatives of the action functional along the fibers. Well, that by definition is, and evaluating those on at the lift, that by definition is C, and then you're taking the time derivatives of both sides. So those are still automatically equal. And these guys down at the bottom, that's this equation we proved up here. Whew. So we get the conclusion that the Euler-Lagrange equations hold if and only if the second Hamiltonian equation holds, and the first Hamiltonian equation was automatic from our set. All right, any questions? Pouring myself another cup of tea. It's dangerous, I know. Let me just note here, I wrote out my Hamilton's equations in coordinates, but there's a coordinate-free expression for them, that the derivative of a function with respect to time is its Poisson bracket with the Hamiltonian. So you kind of, right, the part of what I'm trying to argue here is this principle of least action actually gets you the symplectic form. And it might take a moment to think about, well, wait, why does this tell me what the symplectic form is? And it's built into these Hamilton's equations. So if I'd had a different symplectic form, I would have had a different version of Hamilton's equations, right? So these being Hamilton's equations is equivalent to the symplectic form is the canonical symplectic form on the cotangent bundle. Because it's exactly telling us that the relationship between the differential of dH and the Hamiltonian vector field. So secretly, And these equations determine the symplectic form. So in theory, you could kind of try to solve for this symplectic form by saying, well, x dot and c dot, well, maybe it's not, it's kind of this particular partial derivative application of partial derivatives, which would correspond to some other symplectic form. And then I would go through what the Euler-Lagrange equations tell me. And then they would say, oh, it's exactly that H1 and H2 I wrote above. It's exactly the canonical symplectic form. We might even end a little early this time because all I have left is sort of philosophical musing. So this tells us that Lagrangian and Hamiltonian mechanics are equivalent. And of course, in this course, this might seem like kind of a weird digression, right? I could have just done this course and never mentioned Lagrangian mechanics, and you would know essentially the same amount about symplectic geometry you had before. But, you know, I think to most physicists, Lagrangian mechanics is actually kind of the most natural thing. I think, you know, usually when I talk to physicists, like the first thing they look for is what's the Lagrangian? And Hamiltonian mechanics is this kind of weird alternate thing that might be useful occasionally, but it's kind of an odd thing to do. I sort of, you know, I was doing some research on this, and, you know, like if, at least when I was looking through, what you always encounter are people being like, well, I mean, obviously everybody loves Lagrangian mechanics. Why do people do this other weird Hamiltonian thing? And people trying to justify, no, Hamiltonian mechanics is good. Whereas this course has been, you know, exactly the opposite approach of, well, yes, obviously we want to do Hamiltonian mechanics. Oh, and there's also this weird Lagrangian thing you might also do. So, you know, I feel like I should kind of defend Hamiltonian mechanics a little bit, because there are things you could do in it that you can't do from a Lagrangian perspective. You can do coordinate changes, which combine positions and momenta. You can apply Nutter's theorem, which tells you that you get symmetries from conserved quantities, which is going to lead us to moment maps and symplectic reduction. And it's got kind of a more natural connection to matrix quantum mechanics. And well, people tell me it's important for statistical physics. But Lagrangian mechanics is important too. So don't sort of come away from this course thinking Hamiltonian mechanics is the only thing I should do, because Lagrangian mechanics is kind of based on this more basic fundamental principle of least action. It actually is often easier to use for these problems of things moving around with some constraint. And it also kind of leads to these important ideas in quantum mechanics of like path integrals, right? So somehow Hamiltonian mechanics leads you to matrix mechanics, wave functions, Schrodinger's equation, whereas Lagrangian mechanics leads you to path integrals, Feynman diagrams, all of that stuff. Are there any quick questions? Because I realized I forgot about the stuff I was going to say from last time. I'm sorry. I meant to go back to my notes from last time. So this will kind of be the ad for Hamiltonian mechanics. So remember the thing I didn't have time to talk about last time, and I'm sorry, it just sort of, in OneNote, it was like too complicated to try to copy this much of the page and move it into the other page. So I'm sorry, it completely slipped my mind that we hadn't had time to go through this in detail last time. So one of the really important things you can do in Hamiltonian mechanics that makes no sense in Lagrangian mechanics is you can find a completely integrable system. So you can start with a Hamiltonian system, a manifold, symplectic form, a function, and you can find half the dimension many functions that Poisson commute with your original Hamiltonian, with the first one being the Hamiltonian, which are sort of independent from each other in the right sense. In this Poisson commuting, this is sort of really important, and there's no way to say that in Lagrangian mechanics. And I mean, these functions might not even really make sense there. So this kind of integrable system approach is like one of the key things that makes Hamiltonian mechanics useful. All right, and the examples I had last time, well, if you just have a particle moving around in Rn with no potential energy, then its Hamiltonian is just the kinetic energy. And it commutes with all of the different components of the momenta. Now, in order to get exactly this version of a Hamiltonian, a completely integrable system, you have to throw out one of the components of the momenta and replace it with the energy function. But what we find there, right, since all of these PIs Poisson commute with H, they don't change with respect to time, they're conserved, and we get conservation of momentum. On the other hand, if you have the harmonic oscillator, what you can measure is essentially the energy in each of the different orthogonal components. So the Hamiltonian is a sum of dot products coming from the kinetic energy and then the potential energy, which depends on the distance from the origin. And then the sum of the contributions from each one coordinate, those all Poisson commute with each other, and they give you an integrable system. And the thing I had meant to get to last time and just didn't have time, so let me try to say my point in 4 minutes, is whenever I have a completely integrable system, I can think of that as a function to Rn. And one of the key things that's going to happen is when I evolve with respect to time, I stay on that fibers of that map. So that's pretty interesting on its own. But there's sort of another important part of this, which is, well, it's not just the Hamiltonian vector field of H, which is tangent to this fiber. The Hamiltonian vector fields of all the Fi's are. Okay, so let me just write this in words. XFI is tangent to F inverse of C. So if we choose C to be a regular point, a point where you should think of that meaning is at every pre-image, the differentials of F1, F2, F3, etc. are all linearly independent. So we've required that those were linearly independent generically on our manifold M. And a regular value of the map is one where that happens at every point on the fiber. And some basic theorems of differential topology show that regular values have full measure. So there are lots of them. So if I have a regular value, this pre-image is a manifold, submanifold by the implicit function theorem. And its tangent space, well, that's the kernel of the derivative map down to Rn. So it's the symplectic orthogonal to the, sorry, it's the perp to the spans of the differentials of F1 up through Fn. So this is just kind of general stuff about a regular value of a function to Rn. Right, the tangent space to it is just the kernel of the derivative. And the derivative, you can think of the components of the derivative as d of f1, d of f2, d of f3, etc. So being in the tangent space to that level set is just being perp to all of those guys. So if you think about what this means in terms of Hamiltonian vector fields, that means the tangent space to y is the symplectic orthogonal to the span of the Hamiltonian vector fields, because the symplectic inner product of these Hamiltonian vector fields, I can interpret that as a Poisson bracket, so it's 0. These Hamiltonian vector fields span a Lagrangian subspace, and for dimension reasons, that has to be the tangent space to this fiber. So this is kind of a beautiful thing about completely integrable systems. I have this fiber, and the Hamiltonian vector fields can move me in all directions on the fiber, all possible directions on the fiber, because there are so many of them. So this Y, it's Lagrangian submanifold. And if these vector fields x f1 up, f1 up through x fn are all complete on this fiber, then that means each one of them has a flow. And because the functions Poisson commute, the vector fields have trivial Lie bracket, and so the flows all commute. And those commuting flows, well, those give you an action of the group Rn. We're going to talk next time about actions of Lie groups in more detail, but this is one example of one. So if I just had one vector field, I always get sort of a nice flow as long as it's complete. If I have n vector fields and they all have trivial Poisson brackets, then I get n commuting flows. So this is just a fact about n tuples of vector fields with trivial Lie brackets. One way to get those is to find a completely integrable system. All right. I am out of time. Let me just say really quickly, that means that if I sort of start at some point in Y, well, there's a subgroup in Rn, which is all the stuff that brings me back to Y. And the submanifold Y is just Rn mod that subgroup. It's going to be a discrete subgroup for kind of simple topological reasons. So I'm going to get something that looks like some number of directions that look like R and some number of directions that look like S1. Basically, it depends kind of how big a subspace the subgroup A spans. So with the free particle, right, well, these vector fields, the Hamiltonian vector fields we get is just all the spatial translations. And so I can just move around in space, leaving the momentum unchanged at all points. And so I just sweep out a full Rn. But on the other hand, in this harmonic oscillator, what's going to happen is I have sort of a circle in each one of these planes where the energy sort of in that plane is fixed. And I'm going to get a torus, which is the product of all of those different circles. So a level set of this function fi, just in terms of the pi qi plane, it's just a circle in that plane. It's some, or I should say ellipse, but topologically it's a circle. And I'm just getting the product of all of those circles. All right. And I can get things that are in between, where I get some number of directions that are full copies of R and some number of directions which are S1s. Locally on Y, this gives us what are called angle coordinates, and you can complete these to Darboux coordinates that are called action coordinates. And this is actually like, you know, an important thing to do in like celestial mechanics. You're interested in solving some system involving how planets move around, and it's actually useful to find angle action coordinates. All right, well, I'm over time already, so let me let me stop and give you guys a chance to ask questions, and I guess I will catch up on the chat. I'm sorry that I wasn't watching it.
A quick question about the angle and action angle coordinates.
Yeah.
As you stated it, excuse me, the angles are the the time along one of these vector, along one of these vector fields that keep you on a conserved quantity, right? So these angles, they don't have to be periodic unless you happen to be in a unless you're, they can be periodic or not periodic, right?
Yes.
Like, you know what I'm saying, kind of?
Yeah.
Okay, so because the word angle kind of makes me think, wait a minute, they're not literally angles, right?
So yes,
they can be.
The name angle was inspired by the case where you go in a circle. So that is what it was driving at.
Right.
But yeah, you need some kind of restriction to make sure that you're a torus. I mean, somehow, like, it being a torus is the most kind of important case. As Canis de Silva notes, like, if any one of your any one of the functions in your integrable system is what's called proper, and proper means that the preimage of a compact set is compact, then you'll be guaranteed that the fibers are tori.
Oh, that's interesting.
How, like, right, this example of a free particle, it's of course it's an important example, but it's kind of degenerate, right? Your particle can just fly all over the place in Rn, and somehow that's what you're seeing in the structure of this integrable system, right? And it's much more, somehow it's I think in practice, it's kind of more important that you have these kind of bound systems where you can't just fly off to infinity.
Yeah. And is it just the system that determines it? Like, for example, is there an example of a compact symplectic manifold with non-compact, what's the word I'm looking for? Lagrangian, not tori.
No, because any function on a compact manifold is proper. If I have a smooth map from a compact manifold,
Rn,
the preimage of any point is going to be closed, and right.
So you always have
tori map from a compact topological space is automatically closed, I think, as long as the image is Hausdorff or something. So, like, you're always going to get. So the thing that can happen is, like, a generic fiber will give you a torus, but then there are, like, fibers where things degenerate and you get something worse.
The non-regular points will give you weird things, right?
So yeah, I mean, it's sort of it's tempting to think that you could get something like if you have a torus, well, it's better to kind of think of that as being cut up into here. If you travel at an irrational slope, right, you'll get an orbit that's dense in the torus but never closes up.
Yeah, I was kind of wondering if things like that could happen, basically.
But you'll know, like, that's not the level set of a function.
Right.
So sort of being the level set of a function forces a kind of nicer behavior.
I see. I see. Yeah, and there's also sort of weird examples of foliations of compact manifolds by non-compact leaves, like the Rabe foliation.
Sure. I mean, for example, this case with the torus, what's happening here, this is a symplectic vector field which isn't Hamiltonian.
Yeah. It's exactly what it is,
like,
right?
Somehow the ability to do this, I think, exactly depends on your vector field not being Hamiltonian.
Got it. Interesting.
Well, like, on a surface, if you have a function, you think of it as the Hamiltonian function. Well, you've already cut things up into curves by the level sets of the function. And all you're going to do is travel around that level set when you apply the Hamiltonian vector field. So you're never going to get one of these crazy dense orbits because you have to stay on a level set. So yeah, Hamiltonian things are nicer than just general symplectic things. It didn't seem like there were really any questions in the chat.
I had one kind of vague question.
Mm-hmm.
Going back to when you were saying kind of, when you're doing symplectic geometry, like just as pure maths, you kind of only think about this Hamiltonian stuff. Are there any examples where it's useful to think in Lagrangian terms in pure symplectic geometry?
That's a good question. I honestly don't know. I mean, probably not, because, you know, most things which are kind of interesting from the perspective of symplectic geometry, like one doesn't want to be constrained to think about cotangent bundles, right? So as I said, I read this whole paper that was like about the philosophy of science and, you know, about like why the Lagrangian formalism is more natural. And I think kind of what it boiled down to is somehow any action functional you should really be able to think about as kind of a physical situation. And there are lots of functions on your symplectic manifold which might not correspond to anything physical. So, you know, I don't know for sure. That would be an interesting question for a symplectic geometer. But, you know, somehow just the fact that it kind of only makes sense for a cotangent bundle makes me worried right off the bat.
Yeah. Okay, thank you.
Mm-hmm.
I had a question that maybe Aiden set me up for. It's an easier question though. So when I think of symplectic geometry, when I was reading the notes and stuff, I'm actually surprised that anybody who wouldn't be at least lumped into the category of mathematical physicist or physical mathematician would want to study symplectic geometry anyway. Like, what would a pure mathematician with no interest or motivation by physics want to do in symplectic geometry? Would it just be like low dimensional topology, or?
Yeah, I mean, that's an interesting question. And, you know, I think there's an element of, yeah, I mean, most of the interesting stuff in symplectic geometry, if you get right down to it, there's some sort of physical motivation for it, right? Now, many sort of practitioners of it might not really know very much physics, but, you know, somehow like you probably would wave your arms and say something about QFT if you're going to try to motivate it. Yeah.
I mean, lots of pure math is motivated by physics. Like Riemannian geometry is the study, you know, originated in the study of sailing around on the curved ball of, you know, Earth and stuff.
Sure.
So it's sort of like, yeah, just because it originated in physics doesn't mean that it's not like pure or something.
Sure, of course. Yeah, I mean, I think there are some things which are pretty far. For example, there's this algebraic theory of symplectic singularities, where basically, like, you know, if you look at singular algebraic varieties where the smooth locus has the right kind of symplectic form on it, then like the variety needs to have certain algebraic properties that, you know, don't necessarily hold. And, you know, so there's sort of like, there are interesting theorems about symplectic singularities which don't have any obvious relation to physics. And if you were just interested as like an algebraic geometer in singular, like what kind of singularities varieties could have, it would still be interesting for you.
Right.
Now,
Like I had imagined that if I had to concoct something in reverse, it would be somebody who was interested in complex geometry or something like that and learned about Euler manifolds and then tried to figure out if there was a thing that existed that wasn't, you know, complex.
Yeah.
Or, yeah, that had, you know, the
right.
missing property.
No, the danger with that is that it's kind of very easy to kind of skate into this mirror symmetry world, right?
Yes.
Like, so, you know, I mean, there definitely are like people who are interested in symplectic topology where there's no super obvious link to physics. You know, all of this whole field of symplectic capacities and all that stuff. I'm sure you could somehow tie that back to physics if you wanted to. You know, so for example, I mentioned this on the first day, there's this kind of question of if you take a ball of some radius and then a cylinder whose radius is a little bit smaller, you know, can you symplectically embed the ball in the cylinder? It's like an interesting mathematical question, which, you know, has no obvious physical significance. You know, I'm sure you could say something about like, oh, some problem where you're interested in a ball in phase space and a cylinder in phase space, and whether you can, you know, do some, have the ball evolve over time to sit in the cylinder, but it's sort of a purely mathematical question. And that kind of ilk of things was very interesting. That's kind of the most obvious example I can think of.
I wanted to
also like, we'll talk about this a little bit, like symplectic geometry, you know, plays a pretty important role in representation theory. And of course, again, like you can connect it to physics if you want to, but like you don't have to. You could be interested in kind of purely representation theoretic or combinatorial questions, and just think about like symplectic geometry. And we were kind of talking about toric manifolds, right? Which, you know, combinatorialists are very interested in. And well, like physicists who think about like quantum field theory like to use them as kind of test objects, but there's no obvious, like, certainly you could be interested in them and not think they have any obvious physical significance. That's probably a good example.
I was like, are we going to get a chance to talk about like floor theory and Fukaya categories and all the like kind of fancy schmancy topology stuff?
You know, my aim was to say something about that. I mean, I think that's now kind of such an important part of modern symplectic geometry that it would be malpractice to say nothing about it. On the other hand, like, right, that could be many terms worth of classes on its own. So like,
yeah, let's do it.
Very limited. So yeah, I mean, that's sort of one of, you'll note on the webpage, right? There's kind of, at some point toward the end of February, my like list of topics we're going to cover stops, and I should start adding some more on there. But I wanted to sort of see how we did in terms of speed. All right, I think I'm gonna stop the recording.